Okay, let's talk a little bit about functional groups in organic chemistry. It's important that all organic chemists recognize and know some functional groups. And a functional group is defined as a characteristic group of atoms bound together and they possess a predictable chemical behavior. And what that means is if we see a functional group like an alcohol, so we'll start with what's called an alcohol. And if we have an alcohol, we recognize that it has this functional group. So it has the hydroxyl here. So we call this a hydroxyl. And when that's bound to a carbon, like in this molecule, which is methanol, we call that functional group an alcohol. And methanol is the simplest possible alcohol. And what's interesting is that a seasoned organic chemist can look at that functional group in methanol, the alcohol functional group, and can predict the chemical behavior of that alcohol. Now, methanol is the simplest possible alcohol. Now, what if we have something that's a little bit more complicated than methanol? What if we had a molecule like this? And this molecule is called retinol. And this looks like a pretty big, intimidating molecule when you look at it. But an experienced organic chemist will look at this molecule and say, well, I see a lot of carbon and hydrogen bonds, which are non-polar bonds, but look at this, I have this hydroxyl over here, which means that this compound, retinol, has an alcohol in it. So this functional group is an alcohol because that hydroxyl is bound to this carbon. Something that we're going to see a lot in this video is R, the capital letter R, and R refers to the remainder of the compound, usually carbon and hydrogen atoms. We call those alkyl, or sometimes they can be aryl groups. So what the R means is this. So let's say I draw that methanol molecule again, CH3OH, and of course that's the condensed structure of methanol. If I draw the entire Lewis structure of methanol, and I even include my lone pairs here, so these are the exact same thing. One is the Lewis structure, the one on the right, the one on the left is the condensed structure. I could also draw a bond line structure for that, where I just draw a line and my OH here, which represents my alcohol functional group. But sometimes if we're dealing with a big molecule and we don't want to include the alkyl portion, so this is a methyl group and all three of these are all methanol, what I would do is I would simply use R, and that means the remainder of the compound. So you're going to see that a lot throughout this video is the use of the capital letter R, which again represents just an alkyl or an aryl group. So let's get started in taking a look at some common functional groups that you should be aware of. The first one is an alcohol, and these are in no particular order. And an alcohol is represented by this OH, which we call a hydroxyl. So when you see this OH or a hydroxyl bound to a carbon, we call this an alcohol. A common example would be what I showed you before. If I have CH3OH, this is methanol. It's sometimes called wood alcohol. If I have an ethyl attached to that hydroxyl, this is also an alcohol, and this is called ethanol, and this is the alcohol that is found in alcoholic beverages like beer and wine. And if I have an isopropyl group attached to a hydroxyl, this is called isopropanol, or sometimes we call it isopropyl alcohol, and this is rubbing alcohol. So these are some examples of alcohols, and you have to be able to recognize the alcohol functional group. The next one is an aldehyde, and the aldehyde is represented like this. So we have the remainder of our compound, then we have a carbon doubly bound to an oxygen, and then also attached to that carbon we have a hydrogen. So this is an aldehyde. And a simple example of an aldehyde, in fact the simplest possible aldehyde, would be to just have a hydrogen for our R group, and this is formaldehyde. And if you've ever studied biology, you would know that formaldehyde is sometimes used as a preservative. Another example of a simple aldehyde would be this. If I have a methyl group and then I have my aldehyde functional group, this is called acetaldehyde. aldehyde. And this aldehyde is partially responsible for the crummy feeling you get if you've ever had a hangover. So you have to be able to recognize the aldehyde functional group. The next one is an amide. Sometimes people call it an amide. If you've ever worked with a British scientist, sometimes they'll call it an amide. Anyhow, so an amide has the generic formula like this. So we have the remainder of our compound. We have a C double bond O. We call that a carbonyl. And then we have a nitrogen. And that nitrogen can be bound to two hydrogens. If we have this kind of layout, we call this a primary amide. If that nitrogen is actually bound to one hydrogen and one carbon, so I'll put in one R group here, we call this a secondary amide. And you can probably guess what a tertiary amide is now. So if I put in my carbonyl and my nitrogen here, okay, so I have my two carbon-based groups here. So this is called a tertiary amide. And before we move on and look at other functional groups, I just want to point out one trap that I've noticed students falling into sometimes, is that when you look at functional groups, you have to look at what I call the 30,000 foot view. So you have to look at the entire picture before you make a judgment as to what the functional group is. So later on, we're going to learn what a ketone is and what an amine is. And sometimes students will look at the amide functional group, which I have shown down here, and they'll just zero in on one part of the functional group like this. They'll circle this and they'll say, this looks like a ketone, and then they'll circle this part or put a box around this and they'll say, this looks like an amine like this. Well, that is absolutely incorrect. Okay, that is totally incorrect. When you're looking at a functional group, you have to evaluate the entire thing, and you notice that you have the C double bond O, again we call that a carbonyl, and then we have the nitrogen bound to that, and that's what constitutes an amide. So you need to know primary, secondary, and tertiary amide, and you have to be able to recognize those and to be able to label them if they were in a molecule. Another thing about amides is that if you ever get to study proteins or peptides or enzymes, you'll see that amino acids are held together in proteins and enzymes using amide bonds. The next one is a carboxylic acid, so carboxylic acid. And carboxylic acids are organic acids. They are not strong acids like sulfuric acid or hydrochloric acid. They are acids. They do donate a proton. According to the Bronsted-Lowry definition of an acid is a proton donor, and carboxylic acids do donate protons. They're just not nearly as strong as strong acids like nitric acid or sulfuric acid. So anyhow, here's the generic structure of a carboxylic acid. And a common carboxylic acid is, if I replace that R, if I just have a methyl group here, so I have my carbonyl and I have my hydroxyl here, all bound to this same carbon here. This is called acetic acid. Acetic acid is one of the components of vinegar. Another carboxylic acid, just kind of off the top of my head here, would be this one here. So if I put an ethyl group, and then if I have we call this a carboxyl, so my carboxyl here on my carboxylic acid. This is called propionic acid, and this is the acid that is responsible for giving the tang in Swiss cheese. And so there's the carboxylic acid. So we call this part the carboxyl group sometimes. But when you put it all together, the functional group, we call that a carboxylic acid. The next functional group is an ester. It's not a woman's name, okay? An ester functional group. And the structure for an ester kind of looks like a carboxylic acid in that we have our R, then we have our carbonyl, then we have an oxygen attached here by a single bond. But instead of having a hydrogen attached to this oxygen, we have another R. I'm going to call it R prime. It could be the same as the first R, or it could be different. But this R must be alkyl or aryl. It cannot be a hydrogen, okay? If it was a hydrogen, then it would be a carboxylic acid. So there we go. So there's our ester. An example of a common ester would be ethyl acetate. So if I draw the structure of ethyl acetate, I have my methyl group here, and then I have my ethyl group over here. So this again is ethyl ethyl acetate. Ethyl acetate has several uses. It's commonly used to perform what are called extractions in organic chemistry labs. So something interesting about esters is that many of them have fruity smells or good smells. And this ester that I've drawn here in red, this is called isoamyl acetate. And it has the smell of banana or pear, so a nice smelling compound. So esters oftentimes have fruity smells. The next one is an ether. An ether. So an ether has the generic formula where I have an alkyl or aryl group, and then I have another alkyl or aryl group, and I have an oxygen in between the two of them. And an important thing to note is that neither of these, so R, we'll put here R cannot be a hydrogen atom, because if it was, then you'd have an alcohol, and if they were both hydrogens, well, then you just have water. So an ether, a common example of an ether would be something like dimethyl ether. So if I have a methyl group and then my oxygen and then another methyl group, this is called dimethyl ether. And dimethyl ether is commonly used as a propellant for things like whipped cream or spray paint. Another common ether would be diethyl ether, which we sometimes just call ethyl ether for short. It has a wide variety of uses. It can be used as a solvent in reactions. It can also be used for extractions in organic chemistry. So you have to be able to recognize that when you have two R groups and have an oxygen in the center, you have an ether. The next one is a halide. A halide. So you have to know what a halide is. Sometimes people call these alkyl halides, and that is when we have the generic formula Rx. And if you're wondering, well, there's no element X, well, X can be either fluorine, chlorine, bromine, or iodine, and you will remember that those are the halogens. So if I have an aryl or an alkyl group and I have a halogen directly attached to it, I call that an alkyl halide. For example, if I have a methyl group and I have a chlorine attached to it like this would be called methyl chloride. If I had a bromine attached to an ethyl group, so if I write in an ethyl group here and I put a bromine, this would be called ethyl bromide. And these are both common names. The IUPAC names for these would be chloromethane and bromoethane, respectively. Anyhow, the reason that you need to know about alkyl halides or halides is because they are widely used in organic synthesis. And in organic synthesis, they are commonly used as a way to increase the number of carbon atoms in a structure. The next functional group you need to know is a ketone. A ketone, and the generic structure is like this. If I have a carbon and then I have the C double bond O, again we call that a carbonyl, and I have another carbon here, and we'll write in here that R cannot be H, because if one of those R's is an H, then you'd have an aldehyde. So a ketone is the generic structure that I have shown here. And a common example of a ketone would be if I have my carbonyl flanked by two methyl groups. This ketone is called acetone. That's the common name of it. And you may have heard of acetone even long before you've ever thought about studying organic chemistry, because acetone is the ingredient commonly found in nail polish remover. And so you have to be able to recognize a ketone. The next functional group that you must know is an alkene. An alkene. And an alkene results when we have a double bond between two carbon atoms. So if I put some generic R groups here on my carbon, if I have a double bond between two carbons, this is an alkene. So let's say, for example, if I had CH3 and then I had a CH like this, and then I have a double bond and a CH2 like this. I've kind of drawn this structure a little bit funny. It's kind of partially condensed and partially like a Lewis structure. So if I draw the whole thing out as a condensed structure, it would look like this. CH3, CH, I put in my double bond and my CH2. This is called propene, and propene is used as a starting material to make polypropylene. And polypropylene is a polymer that is used sometimes to make ropes and other materials. So a carbon-carbon double bond, when you see a carbon-carbon double bond, this is an alkene. The simplest possible alkene would be if I have my carbon-carbon double bond and if all of the R groups are hydrogens. This is the simplest possible alkene you could have, and this is called ethylene. And ethylene is partially responsible for the ripening of fruit. So it's a gas at room temperature, and fruits and vegetables can be subjected to various amounts of ethylene to promote their ripening. The next functional group is an alkyne. An alkyne. You have to be able to recognize an alkyne. It takes alkynes to make a world, right? So if I have an R group and then I have a carbon, and an alkyne is a result of a triple bond between carbons. So the alkyne is usually pretty easy to recognize because students usually don't have a problem recognizing that carbon-carbon triple bond. And one of the most common examples of an alkyne is actually the simplest possible alkyne. So if both of those R groups are hydrogens, I would write out the whole Lewis structure like this. If I want to write the condensed structure, in a condensed structure, I never leave out triple bonds like this. And so this is called acetylene. And if you've ever done any acetylene welding, you would know that acetylene is a gas at room temperature and is highly flammable and produces a flame which can be used for welding. So there's an example of an alkyne. Next, we have an amine. Sometimes people pronounce them amine, but I call it an amine. And the generic formula for an amine is to have our R group, a nitrogen, and then we have two hydrogens attached to that nitrogen. If you have this configuration, we call this a primary amine. If you replace one of those hydrogens with another R group, it could be aryl, it could be alkyl, you get a secondary amine. And of course, if you replace all three of those, like this, with alkyl or aryl groups, we call that a tertiary amine. Now you might be saying, well, what if I had no R groups? What if I only had hydrogens? Well, that would mean that you have this molecule, which you probably recognize from general chemistry. This is ammonia, and in fact, ammonia is in a class by itself. It's still an amine, but it's not primary, secondary, or tertiary. It's in fact the simplest possible amine. Another example of an amine would be if I have three methyl groups attached to a nitrogen. I would have, of course, a tertiary amine, and this is called trimethyl amine. And trimethylamine has a fishy odor, and it is the compound that is responsible for what's known as fish odor syndrome. So some people have a syndrome where they're unable to completely metabolize trimethylamine, and it comes out in their sweat, and it gives off a fishy odor, which is called fish odor syndrome. So many amines have sort of fishy or pungent smells. The next one that you should know is an aromatic, or sometimes we call these arene. And the aromatic ring has 6 carbons in it. So we have 1, 2, 3, 4, 5, 6. And we have 3 double bonds which alternate around the ring. So we have double, single, so on and so forth. And I can draw my double bonds the way that I have them shown here, or I can draw them like this too. Either way, both of these structures mean the exact same thing. And this molecule is called benzene. And you may have seen this molecule in general chemistry before, but when we see a benzene ring in an organic compound, we call that an aromatic functional group, or sometimes we call it an arene. Another example would be something like this. If I take my aromatic ring and if I put a methyl group attached to it, this molecule is called toluene. And toluene is sometimes used as a solvent in reactions in organic chemistry. So if I gave you a structure and you saw this aromatic ring in it, you would simply put a box around it, for example. If I asked you to label that, and you would say, okay, well, the functional group here is aromatic, or you could put arene. Either one is fine with me. The next two functional groups I want to look at both involve sulfur. The first one is called a thiol, and a thiol is kind of like the sulfur analog or the sulfur relative to an alcohol. So you remember that an alcohol went R, and then we had our hydroxyl like this, so this is an alcohol like this. If I replace that oxygen with a sulfur like this, this is a thiol. So a thiol is like the sulfur equivalent of an alcohol. Next is a sulfide. And you'll remember that if we have R and then we have an oxygen and then we have another R group, that this is called an ether. Well, the sulfur relative of an ether would be like this. So we have a sulfur between our two R groups, and this is called a sulfide. And so you have to be able to recognize a thiol and a sulfide. Next, we have what's called an anhydride. An anhydride means lacking water, and I'll explain that further on in the class or later on in the class. But an anhydride looks like this. We have our R group, then we have our carbonyl, we have an oxygen, so it kind of looks like a carboxylic acid or an ester so far, but then we have another carbonyl attached to it like this, and then we have another R group. And you might notice this just by looking at the anhydride, but the anhydride can be produced from taking two carboxylic acids and fusing them together with the loss of water. And in fact, that's where the name anhydride comes from, right? It comes from loss of water. And so you have to be able to recognize the anhydride functional group. A commonly used anhydride is actually a relative or a close relative to acetic acid. So you remember that if we have this molecule here, this is called acetic acid. So I'll put this down here, acetic acid. If I were to take two molecules of acetic acid and heat them up and lose water, they will react in such a way to produce this molecule. So my two R groups in my anhydride will both be methyl groups, and I'll end up with this molecule, and this molecule is called acetic anhydride. And the last one is an acyl halide. And sometimes we call these acid halides. So if I have, you might remember that I showed you this. If I have this, we call this a carboxylic acid. So if I had that hydroxyl replaced by a chlorine, I would call this an acyl chloride. Sometimes people call these acid chlorides instead, or an acid halide. Either one works. Organic chemists love to have more than one way to name everything. Anyhow, so an acyl halide, again, sometimes these can be called acid halides. And acid halides can be really handy when you're looking at organic synthesis. In fact, in order to make an amide, which we looked at earlier, if you take an acyl chloride and you react that with an amine, you can produce an amide from that. And that's something that we'll look at later on in organic chemistry. Let's take a look at an example here. So this is just a molecule I made up myself. So if I take a look at this molecule, you can see that we have an oxygen over here, and it's between two R groups. Right here I have a methyl group, here I have a carbon, which is sp2 hybridized, and so this functional group here, this would be an ether. What else do I have? I have a carbonyl here over here, which is flanked between two carbon atoms. I have my CH2, which we call a methylene, and then I have another carbon in my aromatic ring here. So this would be a ketone, right? The carbonyl or the C double bond O flanked by two carbons. Over on the far right, I have a nitrogen attached to one hydrogen, one methyl group, and one CH2, which again we call a methylene. And so this would be an amine. More specifically, it would be a secondary amine. And then you probably noticed right off the bat that we have an aromatic ring in here, so we'll circle that and we'll say that this is aromatic, or we can call this an arene. Either one is fine. let's take a look at this example here. So I would start by looking at this C double bond O, or this carbonyl here, and you notice that on one side it's attached to this carbon, this CH or methine, but on the right hand side I have a nitrogen. So again, I told you have to take that 30,000 foot view when you're looking at a functional group. And since that carbonyl is attached to a nitrogen, this is in fact an amide. And since the nitrogen is attached to this carbon in the carbonyl, there's also a methylene or a CH2 here. There's another CH2 here. This is actually a tertiary amide. What else do I have? I have this CH and it's attached to this hydroxyl. So here I have an alcohol. I also have another oxygen here, which is flanked by two carbon-based groups. So I have a CH here and I have a CH2 here. And so this is an ether. And there's one more functional group in here, and it's this secondary amine. So I have this nitrogen attached to one hydrogen and then two carbons. They're both CH2s, and so this is a secondary amine.